Hello and welcome to Ms. Barlow's Chemistry Review. I'm not very good with screen grasp, so please don't judge my voice or anything like that. Now, this would be a good time to grab some headphones, plug those into your iPads, Chromebooks, whatever you are using right now. If you did not bring headphones, totally a-okay. Just make sure the volume is at a low setting or you are away from others and not distracting them. If you are watching this, it's probably because I'm gone. So here are the learning goals for today. I recommend you pause this video now so that you can write those down in your week 2 learning goals. So week 2 learning goals, first one's right off the bat. I already see a typo, which is awesome. Feel free to pause during any point of this video to make sure you are filling in your fill-in-the-blank notes. I understand I might be talking faster than you can write, so hopefully you'll know to do that. So first thing we're going to do today in this review is talk about atoms. Atoms are the smallest particle we can talk about. There are two main regions we're going to focus on, the nucleus and then the shells and orbitals. So if you're looking in this at my mouse, you're going to notice that there is a central region. This has our proteins and our neutrons, and that's our nucleus. All right, and then orbiting around that are the electrons, and they orbit in shells, right, or orbitals, and we're going to talk about that in a second as to what that means. Now, each of these subatomic particles have a charge. Protons, which sound like pro or good or positive, have a positive charge, and those again are in the nucleus. Our neutrons carry no charge, so try to think like neutral. All right, if you're neutral, you don't have one side or the other. So neutral would be no charge, and that's also in the nucleus. Our electrons, all right, maybe like electric is the best way to remember, but these have a negative charge and they float around in the shells or in the orbitals around it. So an example of an atom would be oxygen, but any of our atoms can be found in the periodic table. So this is what I was talking about with orbitals. There are specific groupings and regions for electrons to be kind of just orbiting around our nucleus. They're never in one place for very long. They are constantly moving and bouncing off their environment and themselves. It's not that important for the sake of our class, these orbitals. However, I did want to refresh you depending on how long ago you took chemistry. So now we're going to move into elements, like the periodic table of elements. Maybe you'll recognize this picture in the bottom right from an awesome show. But elements are pure substances that cannot be broken down into any other pure substances. That's important because we'll be talking about these elements bonding together, and so those would not be an element. They can be broken down further, okay? They will only contain one kind of atom. So for instance, this would be gold, oxygen, mercury, chlorine. Again, anything you can find in the periodic table. Now, how should we use the periodic table? It does have a lot of really important information for us, okay? So if you're looking here, the atomic number, which is this guy up at the top, or just the number that they go in order with, this is the number of protons. So this is how we can use this periodic table to our advantage. The atomic mass, so this number, and generally speaking, I'll have decimals with it, is the number of protons and the number of neutrons. Now, make sure you understand these equations because we can do some simple math to determine the number of protons, neutrons, and electrons in each of our elements. Now the periodic table is grouped into families. All right, so if you're taking a look from left to right, this is going to be our alkali metals. These are going to be alkaline earth metals. Okay, this purple middle section, this is our transition metals. Over here, the pink is some more metals. Then we have this stair-step region right here. This would be our metalloids. They're a little bit not quite metals, not quite non-metals. They're somewhere in between. Then we have our non-metals over here. We have our halogens and then our noble gases. All right, not like Downton Abbey noble, but noble gases. All right, for the sake of our class, it's not terribly important to know these, but it will be important to be able to distinguish between gases and metals and non-metals. So the more general regions are important for us. We're going to move into isotopes and ions. So these are two different variants on any of our elements. The first one we're going to talk about is isotopes. So isotopes. Isotopes are the variations of the number of neutrons in our elements, okay? Now, what does that mean? If you're taking a look at the atomic mass on our periodic table, so I'm going to real quickly flip back to our original slide here on that. If you're taking a look at these atomic masses, so the 4.00 for helium, these are averages based off of how we see, sorry about that. These are averages based off of how we see helium occur naturally, all right? They don't always have 4.00 as their atomic mass. It is an average, meaning we add up all the masses of all the different kinds of helium and we divide by that number and we got 4.00. So if you're taking a look at isotopes, okay, we see that they vary in the number of neutrons, all right? Now, recall neutrons, neutral, they have no charge, so the charge of the element is not changing. However, the mass might, because neutrons do carry a mass, all right? So if you take a look at the picture below, these are three different carbon atoms, all right? We have carbon 12, so it has 6 protons, 6 neutrons. Carbon 13, which has 6 protons, 7 neutrons, and carbon 14, which has 6 protons and 8 neutrons. So notice the only thing that's changing here are the number of neutrons. And this percent right here is talking about their percent presence or percent that they occur. So as you can see, 98.9% is the most occurring form of carbon, which is carbon 12. And then we have some others here that are a little bit less likely to occur, which is why carbon's mass is not exactly 12. It's 12.01. All right. Now, isotopes can be radioactive, which just means they are unstable and they emit a form of radiation. If they do that, they're called radioactive isotopes, and they aren't all bad. Sometimes radioactive gets a denotation that's super negative or Teenage Mutant Ninja Turtle-esque, and that's not necessarily the case. We actually use these in a lot of medical treatments and research. So if you've ever gotten an MRI before for an injury, an athletic one, or any other type of scan, you have probably interacted with radioactive isotopes. Now, ions, all right, do not change the number of neutrons, but they change the number of electrons, okay? And ions are positive because they want to completely fill this outermost electron shell. Now, what do I mean by that? If you recall, there are different shells or orbitals. So I'm going to again real quickly flip back to that, okay? And this is the maximum number of electrons in that shell. If an atom, or element rather, has the maximum amount in that shell and no other, so for instance, if an element had in the 3 shell 8 total electrons, then that is the most stable it can be. So atoms want to be like that. They want to be in that stable state. It's ideal. So forming ions can help it achieve that. Ions that lose electrons become positively charged. Now let's think about that rationally. Electrons are a negative charge. So if you lose less negative charges, you will become more positive. Think about if you had -1, -1, -1. What's that? -3. But if you took away one of those, you'd be -2. You're closer to 0. You're becoming more positive. On the flip side, if you gain electrons, you're becoming more negative because you have more negative charges. So in the example below, we have a sodium atom. This is the normal state of it, where you have this 1 electron right here, if you're following my mouse, on the very outside. All right, and when it loses that electron, it is stable. That second orbital or second shell is completely full, and that's ideal. We note that as Na+, because it lost that 1 electron, so it's positive by 1 charge. All right? So how do these ions form? If they're so ideal, how do they form? They form when an atom gives up or takes an electron to fill that shell. All right, so this is a quick review. Ions that lose electrons become positively charged, and ions that gain electrons will become negatively charged. All right. Now, these resulting positive and negative charges actually form a form of attraction. All right. Think like opposites attract, if you've ever heard of that with relationships or magnets or what have you, right? It's the same thing with our ions. If you have a positive and a negative, they will be attracted and form a strong bond. All right, so take a look here. We have our sodium atom with that one extra electron. We have a chlorine that's one away from filling that outermost electron. So what can we do? Sodium can lose an electron. Chlorine will gain that electron. Now we have this electrostatic attraction here, and we form NaCl. Now, does anyone know what NaCl is? Sodium chloride. It is table salt. So this is the process that gives us table salt here. It's important to note that an ionic bond or an ionic compound is always between one metal and one nonmetal. All right, this is because metals tend to become positive and nonmetals tend to become negative. All right, and if you ever remember anything about ionic bonds, again, big takeaway, write this down, highlight it, star it, mark it in your fill-in notes, whatever you need to do. But ionic compounds are a transfer of electrons. Transfer of electrons, all right? Let's see if I can highlight this for you. Transfer of electrons, yeah. So that's a huge takeaway, okay? Don't forget it. Highlight it, mark it, star it, whatever you need to do. Now we're going to talk about a different type of bonding and element interaction. This one's called covalent, all right? Covalent. This is going to occur between nonmetals only. All right, nonmetals only. So it's not like when we had our ionic compounds, metals and nonmetals, it's nonmetals only. And this is where you have a sharing of electrons. So again, if you're going to remember only one thing from covalent, it's going to be that's a sharing of electrons, which is different from a transfer. Okay, think like covalent, like you're cooperative with someone, you're going to share things, right? Covalent means you're sharing electrons. So if you're taking a look at this one, you have hydrogen, and oxygen, and they're going to share these outer electrons over here and here. And it's going to form a double bond. Or sorry, rather a single bond right here made of 2 electrons. So this is a single bond, 2 electrons. All right, and if you don't recognize this one's water. So it's a super important element and it is a covalently bonded molecule. Now, also it's important to note another difference between ionic and covalent molecules. They don't become charged. So ions, remember, you gain an electron, you become negative, lose one, you become positive. This isn't the case in covalent bonds. You are sharing electrons. There's not that transfer. You're not losing or gaining any electrons. You're just kind of sharing them. Those electrons will be equally on your side and on the other atom's side. All right. So if you take a look in the chart below, there are 3 types of bonds you can have. The first one being a single bond. Ignore the yellow. All right, the single bond, which means you're only sharing one pair of electrons. All right, an example of that could be H2, which is just hydrogen. All right, a double bond means you're sharing 4 total electrons. All right, so 1 pair, 2 pairs of electrons, double bond. This example of that would be oxygen. And lastly, you can also have a triple bond. So that means you are sharing 3 pairs. 1, 2, 3. 3 pairs of electrons. So that's a triple bond. Example of that would be nitrogen. So if you look at this picture right here, there are 1, 2, 3 pairs of electrons. They're going to be shared, which means they're spending equal amounts of time on either nitrogen's kind of zone or area. All right. Again, you don't have to worry about this too much in detail or the exact terminology and structure, but I do want you guys to be aware of this stuff for our Unit 1 test. We're going to move into compounds and living organisms, but I can only record 15 minutes at a time. So what I'm going to have you guys do is follow the next link and keep listening.